Hi, my name is Manis and this is CARE. Classic Auto NSATs and Research Explorer is a teaching and research tool that takes a combinatorial optimization problem and lets you explore classical versus quantum approaches, automatically synthesizes in quantum circuits with classic, and visualizes resource trade-offs and noise sensitivity, the things that matter most in an NISQ era. So why quantum? Many real-world problems like network partitioning, logistics, or portfolio selection can be written as QBOs. A popular variation algorithm, QAOA, alternates problem-dependent cost layers with mixture layers. We don't need a quantum computer to learn. We simulate, measure performance, and importantly, estimate resources like depth and qubit gates to understand hardware viability. CARE goes a step further. We hand roll a clear QAOA baseline and we use Classic to synthesize an auto ansatz directly from a high PIMO model. Then we compare. I'll start with max cut. In the sidebar, I said 10 nodes, the edge probability would be 0.3, the QAOA layers will be 2, and there will be 124 shots, and the optimization generations will be 80. And we'll click generate and solve. And first, we'll draw a random graph and compute a classical baseline. Then we run QAOA on a Qiskit error simulator, optimizing the angles. We also transpile and estimate depth, qubit count, and 2 qubit gates, as you can see here. Now the cool part. Classic auto NSATs. We model max cut in Pyomo by classic synthesize a circuit tailored to a problem, and we fetch its resource metric. If a Qiskit circuit is returned, we can also simulate counts, as you can see here with the data. And to make this actionable, we auto-build a compare summary, ours versus classic, depth and qubit gates count so you can see where each approach is heavy or light, as you can see with the depth comparison here and the 2 qubit gate comparison. If a specific 2 qubit count is reported, we show an analytical QAO estimate, about P times E native RZZ or 2 times P times E if decomposed as CX. So you can still get a realistic sense of cost. But resources aren't the whole story. NISQ devices are noisy. Here, we sweep depolarizing noise for a 1 qubit and 2 qubit gates and plot heat maps of the expected cut. This reveals how performance degrades with noise and how increasing P layers interact with that noise. So here we ran a noise sweep with the following parameters, and we have generated a heat map for P1, and there will be another P map for P2. So if you notice how higher 2 qubit errors hurts more, since these gates dominate entangling costs. You can also re-enable re-opt under noise, which is right here, for each grid cell to see realistic noise-aware angle tuning. To compare quality versus cost across layers, the benchmark tab sweeps P and average results. We track mean best cut, mean 2 qubit gates, and approximation ratio versus the classical baseline. We would normally run it, but this takes a little bit of time, so I'm not going to run it right now. Does not take that much time, but not enough for the video. Also, care is multi-problem. Here is knapsack, a classic QBO. We generate random values and weights, solve classically via dynamic programming, and let classic synthesize a knapsack and sats from a PyMO model, as you can see here. We kept all the parameters the same, and this is our naps. So, why is any of this useful? Teams can import or model their optimization tasks, then rapidly assess if a quantum approach is promising or near-term hardware before spending cloud budget. CARE exposes the trade-offs, circuit depth, 2 qubit counts, impact of noise, and how OS Insights NSAT compares to a transparent QA baseline. It's a sandbox for learning and for planning. Thank you for watching. This is CARE. This is my submission to the hackathon. If you'd like to try live, here is the public link. And thank you.